Hi, in this session we will introduce Fourier series. Okay, so what's a Fourier series? Fourier series is basically an infinite series and it is used to approximate periodic functions. Okay, so before we start with Fourier series, we should know what is a periodic function. Okay, so what's a periodic function? A periodic function is basically a function which repeats in certain periods, it repeats after certain periods. For example, your f of x plus lambda would be f of x, where lambda is a positive real number. Okay, we will say that lambda is the period of that function. For example, sin x is a periodic function and it has period 2 pi. Okay, because sin x plus 2 pi is equal to sin x. Okay, similarly cos x is a periodic function, so it has period 2 pi. Okay, tan x is a periodic function with period pi. You can see some examples are there. And similarly, constant functions are trivially periodic because you know that f of x plus c is always equal to f of x is always equal to k, because always the constant value is coming as the result of a constant function. So constant functions are trivially periodic. Okay, there are also complicated periodic functions like heartbeat, okay, and planetary orbits, they are periodic. And similarly you can say about rotating parts of machines, they are periodic. Okay, so but they are not as simple as the sine and cosine, because you may not know the formula of these functions directly. Okay, it may be very complicated or it is not possible to write them. So the real life examples of periodic functions are not so simple as sines and cosines, but the relevance of Fourier series is that any periodic function, however complicated it may, can always be represented in terms of just sines and cosines, okay, which is called the Fourier series. So Fourier series using Fourier series you can represent any complex periodic function using the very simple functions called sines and cosines, and these sines and cosines always has very good properties, like they are infinitely differentiable, you can infinitely integrate them, you can find the integrals very easily, you can compute them, you know the graph of them. Okay, then so they are odd function, they are even function, so many properties are there for sines and cosines which helps you to make computations easier. Okay, so using these functions you can always approximate periodic functions in the real life also. Okay, so that is the significance of this Fourier series. Okay, I hope it is clear. Okay, not only for periodic functions, if your function is defined over any finite interval, for example, suppose you are considering an engineering problem in which your function, you have to consider a function which is defined on an interval from maybe 0 to 10. Okay, so for example, if you are considering heat conduction problem and you have a rod of length 10 meter or 10 centimeter, whatever it may be, so you need to know the behavior of the function at various points, or the value of the function at various points. You can extend this rod as a periodic function by extending this interval here. Okay, so you can take it as 10 to 20, 20 to 30, and you can say that the function will behave same like this function itself. Okay, so you can extend this function in the interval 0 to 10 to infinity, thereby making the function as periodic. Okay, so once it is made as a periodic function, you can always approximate it using our Fourier series of sines and cosines. Okay, once you can approximate it using sines and cosines, you can always predict the value of the periodic function if the function f of x in any point. Okay, that means you can always predict the properties of the function in the given interval of 0 to 10 also. Okay, so even in engineering applications, if your field of study is only finite length, there also you can extend the Fourier series theory there also, because you can extend that given function as a periodic function. So that is why Fourier series is extensively used in engineering applications. That is the significance of this Fourier series. Okay, now what exactly is this Fourier series? Okay, the Fourier series is basically what do you say, a infinite series of sine and cosine functions. That's it. Okay, you know that the simplest periodic functions are sines, cosines, okay, and also the constant functions. So basically the Fourier series is basically an infinite series constrained of just this constant functions, sines and cosines. Okay, suppose you have a periodic function f of x, I can represent this in terms of sines and cosines. How will I represent it? So it is very simple. I will take cos x, then I will take sin x, then I will take cos 2x, I will take sin 2x, I will take cos 3x, I will take sin 3x. Okay, so I will extend to infinity here. So what are these cos x, sin x, cos 2x, sin 2x, etc.? So in sin x, in the given interval 0 to 2 pi, you will have a complete graph of that one here, but in sin 2x you will have two graphs here. Okay, so two entireties will be of sin x will be there in this small interval, and when you take sin 3x, you will have sandwiched 3 sine graphs there. Okay, so that's the meaning of sin x, sin 2x, sin 3, etc. So using these fundamental figures, you can represent any periodic function in terms of this sines and cosines. Now what will be the representation? The representation is very simple. It is a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x plus a3 cos 3x plus b3 sin 3x plus etc., and maybe you can have a constant also. Or the Fourier series representation is given by f of x is equal to a naught plus sigma n is equal to 1 to infinity. I am just writing it in shorthand, an cos nx plus bn sin nx. Okay, so this is called the Fourier series representation of a function, periodic function with period 2 pi. Okay, firstly we will discuss only those periodic functions which has period 2 pi, then we will move on to any period functions, then we will move on to some simpler series also. Okay, so first we will discuss only those functions which has period 2 pi. Okay, those functions which we have which have a different period also has the similar formula. Some minor changes would be there in the formula, but both are similar. We will discuss it in the later session. Okay, so this is called the Fourier series representation. Okay, so the problem which will be given you to you is that you will be given a function. For example, you will be given a function called f of x is equal to x, and they will ask you to expand it as a Fourier series in the interval maybe 0 to 2 pi or minus pi to pi, whatever it may be. So your aim would be to you have to find out the values of a naught, an and bn with respect to this function which is x. So that is the problem. Okay, so when you are asked to find the Fourier series expansion of x, you will have to find the corresponding a naughts, an's and bn's, and those formulas are also there. They are called Euler formulas, which we will discuss shortly. Okay, so that is how you expand a function as a Fourier series. So basically remember, Fourier series is nothing but a series of sines and cosines, okay, so which are used to represent the periodic functions. Okay, so let us now discuss one more thing also. Okay, so these are our graphs of sines and cosines. Okay, so all of them has period 2x, so the graph also will have period 2x. Okay, so as I discussed, this is the Fourier series representation of a periodic function of period 2 pi. Okay, so I hope it is clear. Now how to find this a naught, an and bn? So before we discuss that, let us discuss some simple results which will be helpful in our discussion. Okay, so this is an example of a Fourier series representation of a signal function like this. So suppose I need to represent a Fourier, I want to find a Fourier series representation of the signal function like this. You can see that this is one sine component, there are many two sine components are there, three sine components. So when you add many sine components, ultimately your graph will look somewhat equal to this. Okay, that means using Fourier series of sines and cosines, using just sum of sines and cosines, you can always represent a function like this also. Okay, this is just an illustration of Fourier series addition. Okay, very simple thing. Now some useful identities which will be helpful for your discussion would be this one. So if you please note it down somewhere, these integrals are very standard integrals. Okay, so e raised to x cos bx dx is equal to e raised to x a square b square, etc. Suppose you need to find integral e raised to 2x into sin x dx, what would be the value? It will simply be e raised to 2x by your a here is 2, so 4 plus b here is 1 plus 1 into a sin x minus cos x. Okay, so this is the value. So here a is actually 2, so it is e raised to x by 5 into 2 sin x minus cos x. So these are some standard integrals, study that also. Then now we will discuss generalized theorem of parts also, that also we will discuss now. It's very simple. So again you know that sin n pi is 0, sin cos n pi is minus 1 raised to n. Okay, now I will introduce a generalized concept of integration by parts which will help you to simplify calculations. Okay, suppose I need to integrate integral x square sin 2x dx. Okay, so how will you usually integrate? It will be simply it is x square into maybe cos 2x square into minus cos 2x by 2 minus integral of 2x into minus cos 2x by 2 dx. Again you will have to find one more part. So this is the general usual formula. But the problem with this formula is that if you bring x cube here also, you will have to do 3 integrations. Okay, 3 integration by parts. That makes the computations much more difficult. So what I do is that I will discuss the generalized formula of parts. It's very simple. Suppose I want to find integral of uv dx. Okay, it is very simple. It is simply equal to u into uv1. Suffix will mean integration. So this means the first function into integration of the second function minus, now u dash, you will have to take u dash into b2. This means again I have to integrate this quantity, differentiate this quantity u, that is called u dash, then I have to integrate this quantity v1, that is called v2. Okay, plus again u double dash v3, okay, minus u triple dash v4 plus etc. So this is the generalized integration by parts. Okay, very simple formula. So one thing you have to remember is that always you will have to you will take u as the function which will always go to infinity 0 first. Okay, so for example here, suppose I need to find integral of x cube sine 2x, I will take u as x cube because x cube will become 0 after 3 integrations. So always take u as the function which will disappear after a few differentiations. Okay, that's the one idea, and always keep u and v separate in calculations, otherwise there is a possibility of you making mistake. Okay, for example, suppose I need to integrate this x cube sine 2x. How will I do it? It will simply be x cube into minus cos 2x by 2, that is first function into integral of second function minus 3x square into, again the integral of this function is again minus sine 2x by 4. Okay, don't multiply this into this because you in the next term you may omit a negative sign, so always keep it as separate. Okay, so what's the next step? It will be plus integration of this term, that is 6x, into integration of this term, that is cos 2x by 8, because integration of sine x is minus cos x. Okay, and again next term would be minus 6 into, okay, this will be sine 2x by 16. Again, if you differentiate the 6, it will become 0. Okay, so this is the value of the integral x cube sine 2x. So I hope it is clear, the generalized integration by parts. Okay, so this is an example of generalized integration by parts. This is formula for generalized integration of parts. Please try to do it yourself. Okay, please try to find integral of x square into e raised to 2x dx using this generalized formula. Okay, so this also help you to simplify some computations. Okay, now we will discuss some trigonometric identities also. That is also very much relevant to our discussion. So some ideas are, you know that integral of sine mx dx and integral of cos mx dx from integral 0 some c to c 2 pi. This means either if it is from integral 0 to 2 pi sine mx dx, or if it is from minus pi to pi sine mx dx, it will always be 0. Okay, so it's very obvious because you can see that when here actually the length of the interval is actually 2 pi, which is the period of the function. Okay, so then in that case your sin x would completing a trajectory here, so it will become 0. So if it is sin 2x, it will have two trajectories here, so it will become 0. So generally in this period 2 pi, your sin x is going fully in the first half and coming down the second half also. That means they will get cancelled out, the area would be 0. Okay, or you can use directly the formula itself. So when you integrate this quantity, what is it? It is basically minus cos mx by m in the limits c to c plus 2 pi. So it becomes minus cos m c plus 2 pi, okay, by m again plus cos mc by m. Okay, now this will become minus cos mc plus m into 2 pi. Okay, so basically 2 pi m is the period is there, so this will become simply minus cos mc by m, so it will be cancelled out, so you will be getting the value as 0. Okay, so this is one identity which is useful in computations, and similarly this value you can just check this out, the value of this quantity also would be 0. This is obtained by, you will be using the product rule here. You know that some product rules are there in trigonometry, like 2 sin a cos b is equal to sin a plus b plus sin a minus b. Okay, so similarly 2 cos a sin b would be sin a plus b minus sin a minus b, and you have 2 cos a cos b, that is actually equal to cos of a plus b plus cos of a minus b. Then you will have 2 sin a sin b. So be careful in that formula, it is actually cos of a minus b minus cos of a plus b. Okay, so using that formula you can split this out here and apply the limits, so you will be getting the value as 0. Okay, and similarly one more identity is here, integral of cos mx cos nx dx would be 0 if m is not equal to n. That is also very simple. You can, if you integrate this, it will be simply be 1 by 2 into integral c to c plus 2 pi. So this is actually cos m a plus b, so it is actually cos of m plus n into x dx plus cos of m minus n into x dx. Okay, so or x, okay, x here. Okay, so when you integrate, you will be getting the values as 1 by 2 into sin m plus n by m plus n plus sin m minus n by m minus n in the limits c to c plus 2 pi. Okay. Now this expression is valid only if this m minus n is not equal to 0. So this expression is not valid for m is equal to n. Okay, so this expression is valid only for m not equal to n. That is why they have written it as m not equal to n. Okay, now if m is equal to n, you will have to compute it directly in a different way. Suppose your m is equal to n, this will become integral c to c plus 2 pi cos square mx dx. Okay, so the value of that would be, you can use the familiar in the trigonometric identity as c to c plus 2 pi 1 plus cos 2 mx dx, and you can integrate this. Okay, you will 1 plus cos 2 mx by 2. Okay, that is you are using the formula of cos square theta, which is 1 plus cos 2 theta by 2. That also you can evaluate. Okay, so this is cos mx cos nx dx is equal to 0, and similarly you will have sin mx sin nx dx also will be 0, and cos square mx dx will be pi, and sin square mx dx will be pi. Okay, so these are some some properties of trigonometric integrals. Okay, so this is extensively used for deriving the formulas of a naught, an and bn. For you, derivation is not required, but the derivation is based on these properties of trigonometric functions. Okay, so you know that the Fourier series representation is given by f of x is equal to a naught plus sigma an cos nx plus bn sin nx. Okay, and if you want to find the value of a naught, you would have to cancel out the values of an's and bn's. From this expression, if you need to find out the value of a naught, you should eliminate this an's and bn's. That can be easily done if you look at these properties. That is, if I integrate this function from c to c plus 2 pi, these will become 0. Therefore, the value of a will simply become, so when I integrate both sides with from c to c plus 2 pi, I will get this as c to c plus 2 pi f of x dx would be equal to integral a naught dx from c to c plus 2 pi. Again, integral of an into integral of c to c plus 2 pi cos nx, bn into integral c to c plus pi sin 2 and sin nx dx. Both of them will become 0, only this much will be remaining. Okay, or in other words, this will become integral c to c plus 2 pi f of x dx. The value of that is actually 2 pi into a naught, or the value of a naught is given by 1 by 2 pi into integral c to c plus 2 pi f of x dx. So when you are asked to find out the representation of some function, for example, f of x is equal to x is equal as a Fourier series representation, first you have to write down this formula. Now plug in the value of the f of x into this formula, you will get the value of a naught, substitute it here. Again, plug in the value of an, f of x in the formula of an, substitute, you will be getting that value. So that is the idea of here. Okay, now how will you find the value of an's? That also has a similar approach. What you will do is that you will actually, to finding an, what you will do is that you have f of x is equal to a naught plus sigma an cos nx plus, okay, an cos nx plus bn sin nx. Okay. Okay, suppose you need to find out the value of a. What you will do is that you know that cos nx into cos mx is 0 for m not equal to n, and sin nx into cos nx is always 0. So what I have to do is that I have to eliminate this a naught and also these terms here. Okay, so what I will do is that in order to find a particular n, I will multiply the entire thing with just cos nx. So this will become f of x into cos nx would be there, plus a naught is equal to a naught into cos nx plus sigma an into cos mx into cos nx. I am using a different index so that we are not confusing with cos nx, plus bm into sin mx into sin nx. Okay, now if I integrate it from 0 to 2 pi, from c to c plus 2 pi, this quantity would become 0. Okay, now sin and this quantity sorry, I am multiplying with cos mx into, okay, cos nx here. Okay, so this quantity would become 0, and these quantity will always become 0 except for m is equal to n, and when m is equal to n, you will be getting the value as pi. Okay, so that's the basic idea. The derivation is not required for you, you just need to know the formula, but the formula is coming through this approach. Okay, I will write down the formula for you. Derivation is not required for you, but the formula is coming through this approach only. Okay, so the formula is very simple. It is 1 by pi into integral c to c plus 2 pi f of x into cos nx dx. This is the formula for an. Okay, if you want to find an, multiply your f of x with the coefficient of an, f of x into cos nx, and integrate. That's the value. Similarly, if you want to find the value of bn, it is simply 1 by pi into integral c to c plus 2 pi f of x into sin nx dx. Okay, so these are the formulas. So these formulas are also called the Euler formulas for Fourier coefficients. Okay, so these are the formula of Fourier coefficients. Okay, I hope it is clear. So the derivation is not required, you just need to remember these formulas. Okay, so when you are being asked to expand as a function, for example, f of x is equal to x in the interval maybe 0 to 2 pi as a Fourier series representation. This is the first step, this is the representation. Now you have to find a naught. This is just obtained by just substituting this as c to c. It is here actually c to c plus 2 pi is 0 to t pi as given in the question, and it is x dx. Find out the value. And again for an, again you have to use the same approach, 1 by 2 pi into integral 0 to 2 pi x into cos nx dx. Find out the value, and once you have found out the values of a naught, an and bn, substitute in this expression, and that would be your corresponding Fourier series expansion. So this is how you will do every question from this section. Okay, you will have to obtain a Fourier series expansion. There will be some formulas. Substitute the function into those formulas. You will get the answer and substitute in the final series. Okay, so this is how you will do Fourier series problems. Okay, I hope that is clear. Okay, moving forward, for the existence of Fourier series, the periodic function should satisfy some conditions called Dirichlet's conditions. So only if these conditions are satisfied would there a Fourier series representation would exist. So we will discuss those conditions in a short while after we do one or two problems. Okay. So and similarly one more thing, in some textbooks they will use the Fourier series representation as, they will write it as a naught by 2. Okay, so that they can write this a naught as 1 by pi just like the other ones, ANs and BNs. So if you look at some guides or some other textbooks, they will be using this representation of Fourier series where you have a naught by 2 plus sigma n is equal to 1, an cos nx plus bn sin nx. Okay, so this representation is used in some textbooks. Both representations are just same. Only difference is that there is a factor of 2 in a naught in the usual one, and there will not be a factor of 2 in the other one also. Okay, so in some problems these type of representations are also used. Okay, in some textbooks. Okay, so be careful which representation you will be using. Ultimately the final answer would just be the same. Okay, that's the case here. Okay, so and this is one more idea here. Okay, so and similarly one more tip to improve integration is that sometimes your interval will be simply minus pi to pi. So if you use the properties of odd function of sine, odd property of sin x and even property of cos x, maybe you will be able to simplify the calculations. We will do such problems also so that you will understand it better. Okay, so these are some general overview of Fourier series. Now let us focus on one problem. We will do one problem, okay, and then we will try to understand how to do a Fourier series representation. Okay, so let us find the Fourier series representation of f of x is equal to x in the interval 0 to 2 pi. Suppose this is the question. First of all, write down the Fourier series representation, which is f of x is equal to a naught plus sigma an cos nx plus bn sin nx, where your n varies from 1 to infinity. I hope this representation is clear to you. Okay, now I need to find the value of a naught. What is the value of a naught? It is actually 1 by 2 pi in given in c to c plus 2 pi f of x dx. Your f of x in this problem is actually x, and the interval is 0 to 2 pi. So integral 0 to 2 pi x dx. Now find the value. It will be simply be 1 by 2 pi x square by 2 in the limits 0 to 2 pi. So this is actually 1 by 2 pi into 4 pi square by 2. Pi will get cancelled out. 1 pi is there. 4 will get cancelled out. You will be getting the value as simply pi. Okay, so I hope it is clear. Please correct me if I am wrong. So the value of a naught is pi. Okay. Similarly, find the value of an. What's the formula for an? The formula for an is actually integral c to c plus 2 pi. 1 by pi integral c to c plus 2 pi f of x into cos nx dx. In this case, it is 1 by pi into integral 0 to 2 pi x cos nx dx. Once I integrate this will become 1 by pi into I am using integration by parts. General form it is x sin nx by n minus again it is minus cos nx by n square, okay, in the limits 0 to 2 pi. I hope this is clear. Okay, so first function x into sin nx by n minus derivative of first function x 1 into integral of this quantity again minus cos nx by n square from 0 to 2 pi. Don't forget to keep it separate, otherwise your signs would be different. Okay, when you apply the limits here, when you apply 2 pi, you will be getting sin n 2 pi, which is 0, and here you will have minus cos 2n pi, which is 1. Okay, so you will be getting here it as 1 by n square. Okay, because sin n 2 pi is 0 and cos n 2 pi is 1. So ultimately, when you apply 2 pi, you will be getting it as 1 by n square. Now when you apply 0, you will have this as 0. This one will be cos 0, that is again 1, and it is plus and minus lower limit, so it is minus 1 by n square. So the value is 0. Okay, so very simple. For ans, we have used the formulas of sin 2n pi. Sin 2n pi is always 1, sin 2 pi is 1. Sin 2n pi is always 0, sin 2 pi is 0, sin 4 pi is 0. Similarly, cos 2n pi would always be 1. Okay, because cos 2 pi is 1, sin cos 4 pi is 1, right? And similarly for 0 also, cos 0 is always 1 and sin 0 is always 0. Okay. Similarly, you can also find the value of bn's. So what's the formula for bn? It is again 1 by pi, right? Integral 0 to 2 pi x into sin nx dx. Apply the formulas. It will be 1 by pi into x into minus cos nx by n. Okay, minus x into minus sin nx minus x not x, this is 1 equally minus sin nx by n square. Okay, from the limits 0 to 2 pi. Okay, I hope it is clear. Okay, so x into minus cos nx by n minus of minus sin nx by n square, which is from 0 to 2 pi. Now you substitute the values here. So you will have the values would be so 1 by pi into 2 pi into minus cos 2n pi is again 1. So it is minus 1 by n. Okay, minus sin 2n pi is again 0. Again, if you substitute x0 here, you will be getting this value 0 only. So finally, I think the answer is minus 2 by n. Okay, so please correct if I am wrong. Okay, once you have got these values, substitute it into this formula. So the Fourier series representation would be a naught is actually, I think it is pi here. A naught is pi. So this will become pi plus sigma n is equal to 1 to infinity. The value of an is 0. So this term would be another. The value of bn is minus 2 by n. So minus 2 by n sin nx. So this is the corresponding Fourier series representation. Okay, I hope it is clear. Just write down the formula, plug in the values, and then write it down. So the value of a naught here is pi, a naught is pi, n is 0, and the value of bn is 2 by n, and the Fourier series representation is given by this quantity. Okay, so if you want, you can take 2 outside also, but this is the corresponding Fourier series representation. Okay, so I hope it is clear how to do Fourier series representation. Okay, now for again, in some problems they will ask you to derive the Fourier series representation, and then they'll ask you to deduce some results using infinite series by using this Fourier series representation. So we will be doing those problems also shortly, but I hope it is clear now. Okay, now moving forward, now let us discuss that Dirichlet's condition for the existence of a Fourier series representation. Okay, so what are the Dirichlet's conditions for the existence of a Fourier series representation? Usually they are asking this question for 3 markers. They will ask you to just state the Dirichlet's conditions for a Fourier series representation. It's very simple. One is the function should be periodic, single valued, and finite. It should be periodic and also finite. Okay, and similarly the f(x) can have discontinuities. Okay, so the number of discontinuities should be finite. This is one condition. Number of discontinuities should be finite in any one period. So it can be actually it means count should be countable, but that theory is not required for it. Just think that it should have a finite number of finite discontinuities in one period, and similarly it has a finite number of maxima and minima. Okay, so the theory behind this Dirichlet's condition is not required for you. You just need to know these conditions because they can ask you for 3 markers. Okay, now if a function satisfies these properties, this function could be written as f of x is equal to this not this quantity, I will write this one. This is a different representation, a naught plus sigma a n cos nx plus bn sin nx. Okay, so you can see that the RHS is an infinite series. Dirichlet's condition says that if the function satisfies these 3 conditions, this infinite series would converge to f of x at all points of continuity. Okay, at all points of continuity, this function would converge to f of x, and at all points of discontinuity, suppose a function is discontinuous at a particular point, this infinite series would converge to average of left hand limit and right hand limit. Okay, so it will converge to average of the left hand limit and right hand limit of the discontinuity. Okay, this is basically, this type of theory is basically used in problems in which you will have to deduce some results from the Fourier series expansion. Okay, shortly we will do such a problem. So in that case, when you when you deduce something from the given Fourier series representation, you are actually giving some values to x. Okay, if the values, so if the point x is a point of continuity, the values would be equal to just f of x. If the point is a point of discontinuity, the values would be equal to the average of left hand limit and right hand limit. That's one idea. And for n points also, there is one more condition. If the function is defined at the end points a, b, okay, the series will converge to the average of f of a plus f of b. Okay, because you can see that at the end points, basically this function is periodic. So a b is there, again a b is there. Okay, so this end point is a, this not again a b here. Basically, this another interval also will be there here. Okay, so you can see that this point is potential point of discontinuity. So the value at this point would be equal to the right hand limit at a. So f of a plus the left hand limit of f b minus by 2. The average of right hand limit at a plus the left hand limit by 2. Okay, so that is also one Dirichlet's condition. Which, so basically we will be using these conditions only in problems which have the statement deduce some result. Okay, so in the examination, if they are asking you to write down Dirichlet's condition, just write down this condition and just tell you that this representation is valid only at points of continuity, and for points of discontinuity, this representation would be equal to the average of LHL and RHL at that point, average of the left hand limit and right hand limit at that point. Okay, so that is the Dirichlet's condition. Okay, I will give you the general Dirichlet's condition for a general periodic function later, once you discuss the Fourier series for a general periodic function. This is actually Fourier series for 2 pi periodic function. I will discuss the Fourier series of general periodic functions in the next session, and in that I will give you the general Dirichlet's condition. The condition is just the same, only thing is that the representation would be a slightly different. Okay, I hope it is clear. Now let us do one more problem. So this is a big problem here. Obtain the Fourier series to represent this function 1 by 4 into pi minus x the whole square in the interval 0 less than or equal to x less than or equal to 2 pi. Hence obtain the following relations. Okay, so you'll have to first of all find out the Fourier series now, and in the Fourier series you will have to substitute the values of some x to obtain these identities. Okay, let us try to find it out. Okay, so how will you do it? The first part is very simple. Your Fourier series representation given by f of x is equal to a naught plus sigma a n cos nx plus bn sin nx. Okay, what's the value of a naught? A naught is actually 1 by 2 pi integral, here the interval is 0 to 2 pi, 0 to 2 pi f of x is 1 by 4 into pi minus x the whole square dx. Okay, so just find out the values that will give you your a naught. Okay, so very simple integration. So it is actually 1 by 8 pi into, this is actually pi minus x the whole cube by 3 into minus 1. You can do it in your ways also, you can expand it also, and in the limit 0 to 2 pi, just substitute, you will be getting the values. The values, I think it is actually equal to pi square by 12. Okay, similarly you can find out a n, value of a n also. The formula is 1 by pi integral 0 to 2 pi, okay, f of x into cos nx dx. So this is actually equal to 1 by pi into 1 by 4 pi into pi minus x the whole square into cos nx dx. Okay, cos nx dx from integral 0 to 2 pi. Apply the integration by parts. So it is 1 by 4 pi into pi minus x the whole square into integral of cos nx is sin nx by n minus 2 into pi minus x into minus 1. Okay, derivative of this quantity, it will be cos nx by n minus cos nx by n square. Okay, again plus 2 into, okay, so minus x in minus 2 into, so plus minus 1 to minus 2 into derivative of pi minus x is again minus 1, again we will have 2, okay, 2 into, again this quantity is minus sin nx by n cube. Okay, so this is the representation. Now you substitute the value of 0 to 2 pi. So please do it by yourself. Remember that sin 2n pi is 0 and cos 2n pi is 1. Okay, so using those results we can simplify this. The value of an is actually 1 by n square. Okay, similarly go for the value of bn. The value of bn is actually 0. So your Fourier series representation is simply become 0. F of x is actually equal to pi square by 12. Okay, plus sigma n is equal to 1 to infinity 1 by n square cos nx. Okay, so this is the corresponding formula f of x for the function pi minus x the whole square by 4. Okay, pi minus x the whole square by 4. Okay, now you have to deduce some results. Okay, so now you will have to deduce some results from this representation. This is the representation written in bigger form. So what are the deductions which has to be made? Okay, so one deduction was actually the one deduction question was this one. First question, which was this one. You will have to find the value of 1 by 1 square plus 1 by 2 square plus 1 by 3 square, etc. Okay, so you need to find out the value of 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus, etc. Okay, now if you look at this result, you need to deduce this result is equal to something from this quantity. Okay, now how will you find it out? So actually my required series is there. Only thing is there is a factor of cos x there, cos x 2x is there, cos 3x is there given there. Okay, so what would be the value? The value would simply be if you put x is equal to 0, what will happen? Your f of x will become, your f of x actually is equal to 1 by 4 into pi minus x the whole square. So when x is equal to 0, your value would be pi square by 4. Okay, f of x would be pi square by 4, and your right side would be actually pi square by 12, okay, plus 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus etc. Okay, now if you equate both of them, you will be getting this as pi square by 4 minus pi square by 12. So it is 3 pi square minus, so it is 2 pi square by 12. That's why you will be getting the values pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus etc. Okay, I hope it is clear. So just substitute x is equal to 0 in this expression. Okay, when you substitute your formulas, x is equal to 0 in this expression. Okay, so okay, and remember one thing, your function f of x is actually equal to don't forget that also, 1 by 4 into pi minus x the whole square in the interval 0 to 2 pi. Okay, so when you substitute x is equal to 0, your x is equal to 0 is actually an endpoint. Okay, so this is the RHS of the Fourier series, and the Dirichlet's conditions say that the RHS would this Fourier series would converge to f of x at points of continuity, and at points of discontinuity it will converge to right and left hand limits, and at boundary points it will converge to average of the values at 0 and 2 pi. Okay, so you have this infinite series when x is equal to 0 should converge to average of f of 0 plus f of 2 pi minus by 2, because average of the right hand limit at 0 and left hand limit at 2 pi. Average of right hand limit at 0 and left hand limit at 2 pi. So what's the right hand limit at 0? F of 0 in this case is actually pi square by 4. Okay, right hand side, and left hand side would be pi minus 2 pi, so it is minus pi, whole square is again pi square by 4 only, so pi square by 4 by 2, so you will be getting the value as pi square by 4. So actually we got it as pi square by 4, but you have to be careful here because 0 is an endpoint here. So pi square by 4 would be equal to this result. Now when you simplify this you will be getting this as pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus etc. Okay. Similarly, you can also find out the corresponding values for next results also. So you need to find out the value for 1 by 1 square minus 1 by 2 square plus 1 by 3 square. Okay, so if you want to find out the value of 1 by 1 square minus 1 by 2 square plus 1 by 3 square etc., you need to substitute something here. So you have to put x as something. Your interval is actually 0 to 2 pi. Okay, so I need alternating positive and negative signs here. So if I put x is equal to, so when you will get alternating positive negative signs here, and cos should not be present, so the cos values should be alternatively 1 minus 1 1 minus 1 etc. So which value of x would you put? So you know that cos pi is minus 1, cos 2 pi is 1, cos 3 pi is minus 1. So if you just put x is equal to pi, the function is 1 by 4 into pi minus x the whole square. Okay, so it's a continuous function. So when even x is equal to pi also is a continuous function. So the series would converge to correspondingly f of pi, which is actually equal to 0. Okay, so your f of pi is actually equal to 0, and when you substitute x is equal to pi in this expression, you will be getting this 0 is equal to pi square by 12 minus 1 by 1 square, cos pi is 1 minus 1 plus, okay, cos 2 pi, so it is 1 by 2 square, cos 3 pi minus 1 by 3 square etc. So when you take the series here, you will be getting pi square by 12 is equal to 1 by 1 square minus 1 by 2 square plus 1 by 3 square, etc. Okay, so this is another way of substituting, and that is also, I hope that is also clear. Very simple results, and once you have done that also, you can see the next result. That is obviously easier because in the next result you don't have this 1 by 2 square, 1 by 4 square, etc. So if you observe it clearly, if you just add these two series, you will be getting it as 2 into 1 by 1 square, 1 by 3 square, 1 by 5 square, etc. So that will be equal to pi square by 6 plus pi square by 12. Okay, so you simplify it. So 2 times that will be sum of these two. Therefore, sum of these two, when you simplify, you will be getting the value as pi square by 8. Okay, that way also you can do. Okay, so I hope it is clear. Fourier series representation. Finding Fourier series is very easy. Only difficulty will be there when they ask you to deduce some expressions. But in that case also, usually when you substitute the endpoints of an interval or the middle point of an interval, you should always get the result. Okay, that's the thumb rule here. Okay, I hope that is also clear. Okay, thank you.